So hello everyone and welcome to this next lecture. So in the previous lecture, we had analyzed the performance of the Chook converter and we had looked at some basic waveforms. Mainly we had looked at the waveforms of the current, and of course we had looked at the waveform of the output voltage, and we had verified that the output voltage is equal to the equation that we know we can associate with the Chook converter. So in this lecture we're going to continue the analysis, and this time I'm going to look at the decoupling capacitor voltage and compare it with the current waveforms. So as usual, before I get started, just a little bit of background that if you are interested in these kind of video lectures, but you do find these video lectures a little too light, I have a few comprehensive courses online. I have one course on simulating power electronic circuits using Python, and in this one this describes more or less the entire process of simulation, which includes installing the software, getting started with simulation, and there is also one complete tutorial on how to simulate a buck converter. And besides this, I also have another course which has just been released, and that is on basics of digital signal processing for power engineers. And in this I'll be talking about some basic theory of signal processing, and finally I'll talk about how you can design filters for mainly power applications. So these two courses the links for these two courses are provided in the description for this video. So if you're interested, please do check it out. And besides that, if you are interested in the simulation files but you do not have the time to go through an entire course, or for that matter you do not have the time even to follow along with the video lectures, this link contains the simulation files that you can download and use for your own purposes. So this link is also provided in the description for this video. So now coming back to the lecture. So let me just go over to my file browser, and in the file browser we had looked at some of the currents. So we had looked at a comparison of all the currents. So this was a comparison of all the currents, which is the two inductor currents and the capacitor current. And here there was the inductor currents which were there, and main idea behind showing this inductor currents was to show that the inductor currents actually have the same pattern. Not only do they have the same pattern, they have the same change in the current magnitudes, that is from the lowest peak to the highest peak. And that is the reason why in a Chook converter you can wind these two inductors on the same core. But anyway, that is an advanced topic. I won't talk about it here. Now, before we continue, what I would like to talk about is, I would like to show you that there is one other thing we can talk about. We talked about the currents, but here in the Chook converter there is another very important component that plays another role, and that is the decoupling capacitor. So as I said before, in a Chook converter, the input is never directly connected to the output, right? For example, if you turn on the switch S1, the input voltage will charge the inductor through the switch. At the same time, this capacitor C1 will discharge through the switch and will charge the inductor and charge the capacitor. When the switch is turned off, the input voltage and the inductor will now discharge and will now charge this capacitance through the diode, and at the same time the inductor will freewheel through the diode. So at no point of time is the input connected to the output. The connection happens through this decoupling capacitor. So let's look at what's happening with the decoupling capacitor. So the first thing we need to do, of course, let's add a plot, and of course this plot will be, let's call it decoupling cap voltage. These plots you can name it whatever you want. Remember that finally the plot will be saved as a PNG file with the same name as your plot, removing all the spaces. So avoid using special characters, commas, dots, anything else, because they will all show up in the name of the file otherwise. So we just have to plot voltmeter C1. Let's call this PC1. Save the waveform and let's click on done. So now that this is done, let's start running the simulation. So first thing we need to do always when you run the simulation, go to the terminal and check if you have any error. We don't have an error, so we are good to go. So let's come down and plot this. So we already know from our plots, let's just check out the range for which we plotted. We plotted for 0.4 to 0.401, but I don't think we've reached that far yet. So let's just plot it to begin with. So this is the decoupling capacitor voltage, and this is what you get. So here you can see that the variation in the voltage is fairly high. The reason is simple, because this decoupling capacitor actually takes a huge amount of energy. Remember, it actually takes energy from the input and it provides energy to the output, right? So this capacitor exchanges a lot of energy, and that is the reason why you see the oscillations are so high. So now let's run it again. We should be in a position to run a zoom very soon. So you see now it is beginning to settle down. Very soon we can do a plot of the voltage of the capacitor voltage with respect to the currents. So let's generate that plot to begin with. So first thing we're going to do, let's add a plot, and let's call this cap and inductor plot. And in this, what we're going to do, we will plot the voltage across this inductor in this decoupling capacitor, and we will plot the currents through the diode, or rather through the inductor, sorry. And so, well, actually we should plot it a little more again. It's important to note you can create plots on the fly. You do not have to rerun the simulation. So let's go check it out. Let's see what's happening with this. The only thing about this is, since we are plotting a voltage and a current, it might be necessary to scale one of them. That might usually happen, and yes, we do see it is necessary to scale them. So what I would suggest is, I would scale, like if you look at this plot, the voltage is around 16 or 18. The currents are in the range of 1 to 2 amperes. So what I would do is, I would scale this down by a factor of around 10, so that we bring it down. So let me create another plot. And let me call this scaled cap and inductor plot. And let me plot voltage C1. Only thing here, let me give it a scaling factor 0.1. And ammeter can be as it is. Save the waveform. And we are done. So let me plot this again now. So this is the scaled one. So you can see now it's much easier to comprehend, and we've already reached 0.4. So let's start scaling these. So the first thing we're going to do is, let's scale this one to 0.4. So first thing we can do, just let's look at this voltage, only the output, or rather the energy decoupling capacitor voltage between in this small range, and let's see what's going on. Let me go over, there's the decoupling capacitor voltage, and this is it. So you see, the most important thing about this is, even despite the fact that we have such huge transients in the beginning, eventually the fluctuation is low. The reason why the fluctuation is low is because of the size of this capacitor. As I said, for that, all you have to do is just go back and look at your circuit parameters. And as I said before, in a Chook converter, the energy storage capacitor, so these are the ammeters, the energy storage capacitor C1 is usually comparable to the output capacitor. The output capacitor is usually much larger because that forms the output bus, and if you need a smooth output voltage, it is necessary in order to have a sufficiently large enough capacitor which filters out any ripple, or rather the ripple is minimal. The energy storage capacitor is sometimes as large as half of the size of this output capacitor. The reason is simple. It is because otherwise your ripple in the voltage across this capacitor is going to be very large, and that will affect the performance of this entire converter if the ripple is too large. And you see here the ripple is minimal. This is very important for a Chook converter. For a Chook converter to operate sensibly, we must maintain a large enough voltage across the capacitor to be able to minimize the ripple. So let's go back and view output, and let's just go plot this again. This is the last plot where we are comparing everything together, 0.4 to 0.401. And this is our plot. So this plot will show you exactly what's happening. So you see that it's tough to know because there's no Y zoom. Maybe I should add that feature to have a Y zoom as well. But when the inductor currents are rising, it's important to note that the capacitor voltage is actually falling by a very small amount. The reason is fairly simple. Let's go back to the circuit. When do the inductor current rise? The inductor current rises when the switch is on. When the switch is on, the input voltage charges the inductor through the switch S1, which is pretty obvious, right? Because you see IL1 is the orange line, right? And that increases when the switch is turned on. Now, at the same time when the switch is turned on, the capacitor is discharging through the switch. And this discharging capacitor is charging the output voltage and is charging the inductor. So the inductor current is rising. But the inductor current is rising because the capacitor is transferring energy to the inductor, right? That's what you see in this line. Of course, it's a little difficult. It would probably at this point of time be wiser to go and plot it using Matplotlib. Maybe I will show you how to do that in another lecture. But this shows you that. Alright. Now, when the currents are falling, you will see that this output capacitor actually is rising to a very small amount. And that's also pretty obvious because you see that when the switch is turned off, that is when the input voltage and the inductor are now charging the capacitor, which means the energy in the inductor is now being transferred to the capacitor, right? And at the same time, the inductor is freewheeling through the diode, which means the inductor is transferring its energy to the output capacitor, right? So that the output capacitor can feed the resistive load. So this is when both the currents are falling, and at this time the capacitor is charging. So this is a cyclic exchange of energy, which is what makes the Chook converter work, right? We have decoupled the input from the output, and we have played this energy decoupling capacitor, which now takes energy from the input and transfers energy from the output. It transfers it to the output. So this is how the capacitor plays a role in this filter. Now, of course, I would encourage you at this point of time to try to play around with the value of the capacitor. Try to reduce this capacitor and increase the ripple and see how this operation changes, right? So with this, I'm going to stop this lecture, and in the next lecture we'll bring in open loop control. If you have any doubts, please do post either in the comments or email me or message me on social media, whichever is your preference. Otherwise, I will see you in the next lecture where we will conclude the Chook converter with an open loop control and then start with another converter, which will probably be the Sepik converter. So thank you again. See you soon. Goodbye for now.